Hello all, welcome back to the Predictive Analytics Regression and Classification course. In lecture 13, in this video, we are going to talk about the effect of feature engineering in logistic regression. Here we will try to understand how we can conduct feature engineering in logistic regression. So typical logistic regression model will have a data set D. So typical, it will have a, if you think from a sort of Excel or data frame kind of thing, you have a Y where Y's are like 1 zeros or something like that, and then you have bunch of features x1 to xp. So these are your features, and you have n such rows, 1 2 3 up to n rows, and you have, so that means you have about n cross p x columns and bunch of vectors of y 0 1s. So that is what I have written. So the ith row you have 1 yi and xi transpose, so the I. So now once you have that, then zi equal to xi transpose beta, and once you compute zi, then you put e to the power zi divided by 1 plus e to the power zi. This is sometimes in statistics we call it logit link. In statistics we call it logit link. In ML we call it sigmoid function. And why we call it sigmoid function we will know, but we'll know that why. But I personally feel logit function is much more appropriate name, because sigmoid function, there are other functional form which also follow like a sigmoid function. So sigmoid function, because this behaves like this kind of elongated s, this particular function. But there are, other than this function, there are functions like probit also behaves like elongated function. So probit link can be called sigmoid functions, but in ML particularly logit link is being called as sigmoid function, which is not necessarily a unique thing. So I prefer to call it logit link. And then once you define pi1 and pi0 is effectively 1 minus pi1, and then for pi1 you observe 1 yi value as 1 with probability pi equal to 1, and 0 with probability pi 0, or 1 minus pi1. So here beta, this should be beta, beta is p cross 1. So okay, now this is a mathematical representation. This is mathematical representation of logistic regression. Now the same logistic regression I'm going to represent as in a graphical point of view. Now we have x1, let me use a different color. So this is x1, this is x2, dot 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 xp. So we have x1, x2, xp, and then each of their weight, these arrows represents their weight, and if I multiply them with their weight, so beta naught, this is 1, this is intercept, so beta naught plus beta 1 x1 plus dot 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 beta p xp, let's call it z, and then we are putting it into a sigmoid function. Z is e to the power z by 1 plus e to the power z, that is my p. I'm getting p, and then with some probability I'm getting observing 1, I'm observing 0. So that's my graphical representation of the model. Okay, so now we will try to understand the sigmoid curve behavior of the logistic regression. So logistic regression does not behave like simple linear regression. Instead, it behaves like a sigmoid curve. So what we will try to do, we will try to visualize the nature of the sigmoid curve using some following simulation study. Okay, so we consider predictor variable x between minus pi and pi. So x is a variable which takes value, x ranges value between minus pi and pi. So now what I'm going to do, I'm going to define z, where z is 0.01 plus 0.45 times x plus e, where e is some random number generated from normal distribution with mean 0 and standard deviation 0.3. Now we define a response variable y equal to 1 if z is strictly greater than 0 and y equal to 0 if z is strictly less than 0. Okay. Now ask yourself, pause the video for 5 minutes, ask yourself, is this model a logit model or probit model? I hope you tried it and you got the answer. So it is actually a probit model, because you see E here, it follows normal distribution with mean 0, standard deviation 0.3. Okay, so that means it follows logistic regression with probit link. Okay, so it is probit model. Okay, so not logit, it is a probit model. Now we pretend that actual response variable z is unobserved. This is very important. In our real life, we will never see observe z. So this is my data generation process. So I am just simulated some random numbers from uniform minus pi to pi. Then using this model I generated z, and given z I generated y. Now I will just pretend that I have only y and x, and I will delete all the z values. Okay, so now we will pretend as if we never observed z, we never observed z values. The only data that we have is x and y in D as some data frame, right? So we will just define some data dot frame x comma y as D. Okay, so we model the relationship between x and y now using logistic regression. So we will use GLM function in the stats package of R. So if you do that, turns out that these purple colors point, these are actual observed y for different values of x. These are actual observed values. And this red color that you are seeing, this red color curve, This is actually your estimated P, or probability y equal to 1. Okay, so you can see that this P behaves like a elongated S. That's why it's called sigmoid curve. So the non-monotonic relationship with logistic regression, the elongated S-type behavior, also known as sigmoid curve, is well understood in the literature. If you want to know more about the detail about it, then you can see the chapter 4 of Introduction to Statistical Learning by James, Witten, Tipshirani and Hasty. Okay, I will recommend this everybody to read this chapter. This is a beautifully written chapter. However, elongated S only models the monotonic relationship between X and Y. Here we discuss how we can model the non-monotonic relation between X and Y using logistic regression. So we can model the non-monotonic relationship. Now, why, before going into the how to non-monotonic, so I hope you understood why I am calling it monotonic relationship, because as X increases, so what is the relationship between X and Z? The relationship between X and Z we are considering is straight line, right? And what is the relationship between Z and P? Z and P has an elongated S, and that what we are seeing in X and P. So if you put that is putting it into some sort of a elongated curve, but it is continuously monotonic function. It is not a non-monotonic function. It never been like going up and then coming down. It is always increasing constantly. It is increasing. It is bounded between 0 and 1 because it is probability, but it is continuously increasing. It is a monotonic function. Now, the relationship between X and P not necessarily has to be monotonic. It can be in real data. It can be going up and then make them down. So the elongated curve in the monotonic relationship, so if you just use a simple linear regression, logistic regression, it will only model the monotonic relationship between X and Y. So now we will discuss how can we model the non-monotonic relationship between X and Y. We can do it by using higher order polynomial. How? So previously what we were doing, we were using beta equal to e to the power, say beta naught plus beta 1 x divided by 1 plus e to the power beta naught plus beta 1 x. Now what I am suggesting, why you stop here, you add the higher order polynomial. Here I have added quadratic. You can add cubic or polynomial of order 4, 5, whatever you want, you can put it there. In the equation 1, quadratic equation is being presented to model relationship between X and Z. We can use higher order polynomial model to capture the underlying relationship between X and Z. So the non-monotonic relationship with logistic regression, let us try to capture this behavior. Let us assume that relationship between X and Z are sinusoidal. So we consider the predictor variable between X of X between minus pi and pi. So we simulate the latent variable Z as Z equal to sin X plus error. So error is still following normal. So 0 with standard deviation 0.5, but the relationship between Z and X is for sure not linear. It's a sinusoidal. So how it is? That's how the relationship between Z and X. The latent space has a very non-linear relationship. Now if you, when from Z we simulate the Y's and we plot, that's how it looks like. That's how it looked like. So we had some values here, then we got a bunch of values here, and then we got lots of values here. So because now it is either all values of Z is being converted into Y as either 0 or 1. That's all. And in real life we don't know what is the Z values. So all we have is the values of Y, which is either 0 or 1. So we pretend that we do not know the true relationship between X and Z. Okay. And we simply fit a logistic regression of simple logit P beta naught plus beta 1 X. So that is P equal to e to the power beta naught plus beta 1 X plus 1 plus e to the power beta naught plus beta 1 X. Okay. Now if you fit that, this is fitting a simple non-monotonic elongated S curve. Fine. Monotonic relationship, it's giving you a monotonic relationship, but though we know we have quite a few points here, and the underlying relationship is very non-linear. So we thought, like, we see simple logistic regression models, non-linear but non-monotonic relationship between P and X. Even if between X and Z has a non-monotonic behavior, like quadratic, cubic behavior, sort of sinusoidal behavior. So we fit a cubic relationship between X and Z, X and P, okay, and we decided to go for this beta naught plus beta 1 X plus beta 2 X squared plus beta 3 X cube, and hence the final model is this logit P equal to beta naught plus beta 1 X plus beta 2 X squared plus beta. So final model is logit P equal to beta naught plus beta 1 X plus beta 2 X squared plus beta 3 X cube. And when we fit that model, the P is now nicely non-monotonic and capturing the sinusoidal behavior between X and Y. So we never used Z here. Remember that all we have is only X and Y. Just modeling the higher order feature, we put couple of higher order feature X square and X cube, and the model logistic regression able to model the sinusoidal behavior of relationship between X and Y. So this is about to show that we can use feature engineering technique to capture the non-linear and non-monotonic relationship between X and P or Y. The feature engineering typically helps increasing out of the sample model accuracy. However, we should be careful about the overfitting, because when you put more and more features in your model, so naturally you have a chance that you end up overfitting the model. Okay. So thank you very much. See you in the next video.